So today's unit we'll be talking about the nervous system and neural functioning. So I'm gonna get my PowerPoint pulled up here. We'll get started. Here we go. All right. This, get my pointer. Okay. So again, when we think about the general functions of the nervous system, really three things that we're looking to do. Number one, we want to receive sensory information. So sensory comes from sensory receptors that are located at the ends of peripheral neurons. Number two thing we want to do is have integration. So this is going to occur within the central nervous system, and this can occur at varying levels depending on what the sensory data was. So again, this could involve a simple reflex. So such as like if I touch something hot, I quickly pull my hand away before that message even has a chance to be carried to my brain, because the integration occurs right at the level of the spinal cord. However, if I see something that might be threatening or upsetting to me, I might integrate that at the level of the frontal cortex, where higher order thinking occurs. So again, the site of integration can occur either within the brain or within the spinal cord, depending on what that sensory information was. And then number three is motor signaling. So this occurs in the peripheral nervous system via the motor neurons. Hang on just a second. Okay. All right, here we go. So again, when we look at an overview of the nervous system, again, our major goal is communication. So again, we're going to receive information from our sensory receptors. Then we are going to process that or integrate that information and decide what to do with it. And then lastly, we'll have some sort of response or motor activity. The nervous system is a mystery. This is a system that we don't really know a whole lot about in comparison to many of the other systems. Again, it's believed that we have about 20% understanding of what's actually going on within the nervous system. So super interesting and a lot more to be done in our lifetimes to get a better grasp of, what's actually happening within this particular system. Okay. So when we look at the organization of the nervous system, again, you might already know this from anatomy and phys 1, but the nervous system has two major divisions. We have the central nervous system, which is made up of the brain and spinal cord, and the peripheral nervous system, which is composed of nerves that connect the brain or spinal cord with the body's muscles, glands, and sensory organs. Okay. The neuron is the basic cell type in both systems. So again, both in the central nervous system and in the peripheral nervous system, we will have many neurons located within. So again, when we look at kind of zoom in and take a look at what does a neuron actually look like, here you can kind of get a good look at the structure. So again, we have dendrites, which are located here, cell body, also known as the soma of the cell. Then we have an axon and then axon terminals here at the end. When we think about their function for each of these components within the cell, and again, this is the cell nucleus here in the middle. So the dendrites are going to receive information. This initial segment, sometimes called the axon hillock, is where we decide like what to do with the information that we received in the dendrites. So again, we're receiving both excitatory and inhibitory signals all the time. And then the axon hillock can kind of sum up those signals and decide what to do next. Then the information will be sent down the axon, or the signal will be sent down the axon and be terminated at the axon terminals. And these will have an interaction with could be a muscle, could be another neuron or something along those lines. So they'll have an effect or send their signal on to somebody else. So one thing to keep in mind when we think about the structure and function of a neuron is it's a one-way street, right? So I'm receiving information up here and I'm sending information down here, okay? Never in the opposite direction. It always comes from information is received from the dendrites, summated here at the axon hillock, sent down the axon, and terminated in the axon terminals, okay? So it's a one-way street. Again, when we think about some of the unique characteristics that we see in a neuron, they're also known as nerve cells. So again, that's kind of our basic cell type within the nervous system. They're amniotic in nature, so they don't really divide. Okay, so you're born with a certain number of neurons, and basically that's how many neurons you're going to have. So that's pretty freaking cool. Like, you're just born with a certain number, and that's what you have. And if you kill those, then they don't reproduce themselves, basically. They also have a very high metabolic rate. So they use a lot of calories in order to maintain themselves, basically. And when we think about the other types of cells that we have within the nervous system, the neurons themselves are not the most numerous cells. The glial cells are, and glial cells are going to be like a support cell to help those neurons stay healthy, essentially. Right? So again, we can look at different classifications of neurons. Again, we talked about how they were highly metabolic. They can't reproduce themselves. You're born with a certain number of them. But we can divide them up into kind of three categories. So we have afferent neurons, efferent neurons, and interneurons. And these interneurons actually account for the majority of the neurons that we have, and they're simply connectors. Okay, they're going to lie within the central nervous system, and they're going to connect to other neurons. Okay, efferent neurons are going to send information out of the central nervous system and have an effect on something else. Okay, so they're sending a motor signal. So efferent neurons are also known as motor neurons because they're sending a signal out. Okay, afferent neurons are going to receive information or send information up. Okay, so they're going to receive information, sensory information in the peripheral area, and then they're going to send that information, send it to the central nervous system. So again, afferent neurons, also known as sensory neurons, efferent neurons, also known as motor neurons, and then the interneurons are kind of like connectors. And again, those are going to allow us to connect different neurons to create different paths. Okay, so the next thing I want to talk about is something known as the resting membrane potential. And why the resting membrane potential is important is because it allows us to establish many factors that are essential in order for us to be excitable. Okay, so the resting membrane potential has to be established in order for us to be able to send a neural signal. Okay, and the neural signals that we're going to send are also known as action potentials. Okay, so let's take a look. So again, I'm going to set the stage with varying components associated with the resting membrane potential first. We must understand what's going on at rest in order for us to then be able to apply some of these principles to understand what happens when we want to send a signal. Okay, so first thing we want to understand is that the membrane has two types of channels. Okay, let's see if I can draw on my PowerPoint here. And I apologize in advance. I wish I had like a touch screen that would make things a lot easier, but I don't. So I'm going to be using my mouse. So pardon my lack of artistic ability. So imagine this is the cell. Okay, so we're looking at what's going on inside the neuron in comparison to what's going on around it. Okay, I have two different types of channels. I have a gated channel. Okay, imagine that those are two little gates that come together. That's your gated channel. Okay, and a leaky channel is basically like I have like a little hole basically in the side of the cell. Okay, so gated channels and leaky channels. The gated channels are going to open and close based on a particular stimulus that is provided. And the leaky channels are always open. Okay, so think of them as like a little hole in the wall, but they're selectively permeable. Okay, so if something's selectively permeable, that means only certain substances can go through this leaky channel. Okay, so imagine that I had these kind of all over the edge of this cell. Okay, and again, we're using this to kind of set the stage for understanding what's going on with the resting membrane potential. Okay, this slide is really important. So when we kind of set the stage again for this resting membrane potential, we need to understand what's going on inside the cell in comparison to outside of the cell. So again, imagine that this is the interior of the cell. Can I write on this black part? Let's see what happens. Nope, it won't let me. Okay, so this is inside of the cell, and this is outside of the cell. And really 4 things to notice when we think about what's going on inside the cell versus outside of the cell. Inside of the cell, we have a high concentration of K+, which is potassium. Outside of the cell, we have a little bit of K+. Outside of the cell, we have a lot of Na+, which is known as sodium. Inside the cell, we have just a little sodium. Okay. Now, it's important that we have these concentration differences. Okay, so we have to have high potassium inside, high sodium outside in order for us to establish a gradient. Okay. Other things to note, inside of the cell, there's a charge of -70. Okay. So again, you can see that it's negatively charged inside and it's positively charged on the outside of the cell. Okay. So far, the important things to know, the charge inside the cell is negative and it's -70 millivolts. Okay. The outside of the cell is positive. Okay. So you can see these positive charges lining the outside of the cell. Additionally, I have a lot of potassium inside, not a lot of potassium outside. I have a lot of sodium outside, not a lot of sodium inside. Okay, so that's kind of the basic setup of what's going on at rest, right? So now remember back on the previous slide that I mentioned something called gated channels and leaky channels. Okay. And here you can see what's going on with these channels. Notice that the leaky channels are selectively permeable. They will allow movement of potassium and sodium. Okay, so let's start with the leaky channels. And I want you to imagine that you are a potassium molecule, okay, and you live inside of the cell. And there is a leaky channel that leads to the outside. And knowing what you know about simple diffusion, right? If I am a potassium molecule and there was a leaky channel, a way for me to move from outside to inside or inside to outside, which would I want to do, right? And because there's a high concentration inside, those molecules want to get out. They want to move down their concentration gradient. And that's exactly what they do. Potassium flows out of those leaky channels, okay? Now let's imagine that you're a sodium molecule. Again, sodium highly concentrated on the outside of the cell, just a little bit of sodium on the inside. And what would I do if I could move across the channel based on those concentration gradients? I would want to go in. There's my excellent arrow. Here's my excellent arrow for potassium. Okay. Right. So again, sodium wants to flow down its concentration gradient, so therefore it wants to go inside of the cell. Okay. The gated channels, here you can see gated channel. Oops. is in the purple, okay? And the gated channel is going to allow 3 sodiums out and 2 potassiums to come in, okay? Now notice that we've only talked about positively charged molecules. Again, you see this positive sign, so potassium is positive and sodium is positive, so we can see that as well. But yet we have this charge, this negative charge of -70. So what the heck? We've only talked about positive molecules. How is it possible that the charge inside is negative, right? Well, 2 reasons why, okay? So again, I want you to now think about this like a bank account, okay? Inside the bank is inside the cell. Outside the bank is like what I spent. Think of it that way, okay? So with that gated channel, I'm spending or sending out 3 molecules, but I'm only bringing in 2, okay? So I have a net of -1 for the gated channels. Gosh darn it. Let me write -1 here. There, okay? So again, I spent $3 and I only brought $2 in, so now I have a -1 with the gated channels, okay? Now these leaky channels, we said they're selectively permeable. However, they're not equally selectively permeable, okay? So basically, like the sodium molecule is molecularly larger in comparison to the potassium molecule, so it's harder for the sodium to move, okay? So I'm only going to bring in like 1, why does it keep doing that? 1 sodium for every 50 to 100 potassiums. I know, I'm sorry about my drawing. Okay, so again, I spent 50 to 100 potassiums. I spent $50 to $100 and I only brought $1 in. Okay, that's with the leaky channels. So huge discrepancy here with ion movement. And then when we think about the gated channels, again, I spent $3 and I only brought $2 in. So I had a -1 here, okay? With the leaky channels, again, I have either a -49 to a -99, right? And that's what allows us to have this negative charge inside of the cell, okay? Again, I think we'll spend some more time going over that, but those are the fundamentals that set up the neuron to have this resting membrane potential. It's essential that we have this imbalance of charged particles in order for us to allow this cell to be excitable, okay? So again, here you can see with the resting membrane potential, -70. Now I'm going to use this little pin all the time. This is great. -70 is where the cell prefers to be at in regards to charge. Different cells might have different resting membrane potentials. So neurons generally range from -40 to -90, depending on how excitable they are. But the important thing to note, just use -70 as kind of your general reference point, and just note that all of them need to be negative if they want to be excitable, if they want to send a signal. Okay. Changes in the potential are going to be due to the movement of those ions that we just discussed. Okay. Again, as mentioned, this just kind of shows you in a chart form the difference in concentration inside and outside when we compare sodium and potassium. Chloride is different too, but don't worry about chloride. Let's just focus on sodium and potassium. Okay. So don't worry about chloride, don't worry about those numbers, right? But again, things to remember. Sodium inside is low, 15, and outside is high, 145. Potassium is basically the opposite of that. So inside is high and outside is low. Okay. So we've established what we need to establish in order to understand the resting membrane potential. Now we're going to look at how we can cause excitability. How can we cause change? How can we send a signal within the nervous system, within one of those neurons? Okay. So when we talk about action potentials and graded potentials, we'll use some of these terms. So depolarization. See, I love this little thing. I wish I had a touchscreen so that I could make like circles a little bit more efficiently. So depolarization involves the resting membrane potential increasing in charge, okay? So it's gonna become more positive in nature. So if I started at -70, I could depolarize to -30, for example, okay? Repolarization is the potential moving back down. Okay, so following a signal being sent, I need to repolarize my cell, which means the cell's charge needs to decrease back to -70 or whatever you started at. Hyperpolarization is when the cell moves in the wrong direction. So if I started at -70, it moves to -90 or something like that. So it's moving away from the resting membrane potential. Okay. So again, depolarization, increase in charge, that's going to be excitatory, get us close to sending a signal. Repolarization occurs after a charge has taken place or after an action potential has taken place. And again, this will allow us to decrease our charge back to -70. Hyperpolarization is when we go below resting membrane potential. So below that -70 gets us further away from being excitatory. Okay. Again, all these terms are used relative to the resting membrane potential. Where did we start at? Okay. So here you can kind of see what that looks like on a chart. So again, remember we're starting at -70. That's our resting potential. Depolarizing, I'm increasing my charge. Now I want my little laser pointer back. Okay, so depolarization, I'm increasing the charge, becoming more positive in nature. Repolarization occurs after a signal is sent, and that allows us to return the charge back to -70. Hyperpolarization occurs when I go further away from resting membrane potential, so I become more negative in nature. Okay. So in order for us to send a signal, we have to create we have to create an action potential. And we can do that in a variety of ways. One of the ways we can do that is to create these little graded potentials. And a graded potential is a change in the membrane potential that's confined to a relatively small region of the plasma membrane. So again, imagine this red thing is my cell. Maybe I'm having some excitatory signals in this section, but the other 80% of the cell isn't getting any type of stimuli, okay? So it's a relatively small portion of the plasma membrane, and that will produce what's known as a graded potential. They're graded because the magnitude of the potential can vary, okay? So it can be super excitatory in this area or it could be a little bit excitatory, okay? So it depends on the level of stimulation that's being received by the cell. Okay. These graded potentials can be positive or negative in nature. Okay, so the stimulus here, you can see it's depolarizing, so it's excitatory in nature. Here you see a stimulus that's hyperpolarizing or inhibitory in nature, so it takes us further away from being able to send a signal. Okay. Again, they're graded. A weak stimulus creates a small change, and then a stronger stimulus will create a larger change. Again, as I mentioned, these can either be depolarizing, excitatory, you see those over here, or hyperpolarizing or inhibitory, and you see those over here. And again, those are all triggered by changes in a local environment. So just a small portion of that cell itself, of the cell membrane. It's not the entire cell being affected, just a small little portion. Okay, so in order for us to send an action potential or an excitatory signal, we need to have rapid depolarization of the neuron's membrane potential. Okay, again, action potentials are needed in order for us to send a signal. And we're going to change our membrane potential from -70 to +30. And how does this happen? We're going to take a look in just a second. But again, remember that in order for us to have an action potential, we have to have excitatory signals that are going to allow us to have depolarization occurring so that we can increase the charge of the cell up to positive 30. All right, how does this happen? Again, I've got a little YouTube clip down here. Please watch the YouTube clip. The guy has a nice accent. It might be good for you to kind of take a look at this. I think he sets up the resting membrane potential well as well. So again, a different kind of viewpoint, but it might be nice for you to kind of check out that link. All right, so what happens, again, as I am receiving excitatory information, I'm going to open sodium channels. Sodium rushes into the cell. That causes depolarization because I'm increasing the charge, okay? So as I open those sodium channels, again, sodium will rush into the cell. And because those are positively charged ions, that allows us to increase the charge inside of the cell all the way up to plus 30, okay? Once we reach plus 30, those sodium channels are going to close, okay? So we've now got this change in concentration inside the cell versus outside the cell, okay? So now we've got a bunch of sodium inside the cell, okay? The next thing that happens is our repolarization, or returning back down. Sorry, that's supposed to be an arrow. And potassium channels open, allowing potassium to rush out of the cell. So potassium leaves. Again, as I'm spending those positive molecules, my bank account will go down. Okay, so I'm getting rid of many positive molecules, so therefore the charge decreases. Okay, so that's basically what happens. So depolarization occurs when sodium channels open and sodium rushes into the cell. Those sodium channels close, and then potassium channels open. Potassium rushes out of the cell, causing the charge to go down, known as repolarization. Okay, so those are basically the two basic steps needed in order for us to send a signal. Okay. We know this is super freaking fast. That's so cool, right? So as brief as 1 to 4 milliseconds and may repeat at frequencies of several hundred per second. Again, if you think about the complexities just simply in sport, for example, right? How quickly can you respond to something that's changing around you, right? Well, that involved maybe millions, definitely thousands of neurons acting together and reacting in a coordinated way after you've integrated a response and come up with your solution to what was happening around you. So I just think that's absolutely remarkable how quickly we can respond, you know, to a particular stimuli. The system is so fast. Okay. The ability for us to generate these action potentials is known as excitability. This ability is possessed in neurons, also produced in muscle cells as well. So our muscle cells need to be excitable in order to respond to a stimuli, and many other types of cells as well. But again, those are two pretty important ones, the nervous system and the muscular system. An action potential, again, is a large change in the membrane potential, and this happens, it's known as an all or none response, okay? So when we say an all or none response, basically, in order for, and again, here's a nice little chart that shows you, you can read through this. This gives you all the details of the things that we've talked about. If you're more of a, you know, you'd rather read it than listen, that's totally fine. So basically what we need to do in order to create this all or none response is I have to reach this threshold level, okay? So once this excitatory signal gets above whatever our threshold is, then the signal is sent, okay? So when we say it's an all or none phenomenon, we are either sending a signal or we're not sending a signal, okay? There's no like small action potentials and large action potentials. We are either yes, we're sending one, or no, we're not, okay? So again, you know, when you think about this, in order for us to send a signal, it's either yes or no, right? So the action potential, in order for it to be all or none, either yes, it's sending, or no, it's not. And if I reach this threshold, then I'm sending the signal. If I don't reach this threshold, then I'm not able to send that signal. okay? And again, we'll talk about how we could modify intensity here in just a second, okay? So 2 other terms to note here. When we think about sending signals, again, once I reach that threshold, I'm ready to fully commit to sending that signal. Before I reach that threshold, it's like, am I going to send it? Am I not? I don't know yet. Okay. And once we reach that threshold level, we will have that depolarization occurring rapidly, followed by that rapid repolarization as well. So the signals are going to be sent. Okay. So once we decide the action potential is going to be sent, there's 2 other terms to kind of identify here. We have an absolute refractory period and we have a relative refractory period. I'm going to use a weird analogy with this, okay? I want you to imagine when you go to the bathroom, right, and you flush the toilet, and then you try to flush the toilet immediately right after. What happens? You're not able to flush the toilet a second time immediately after, okay? That's the absolute refractory period, okay? The absolute refractory period is this time where no new action potential can occur regardless of how strong the stimulus is, okay? And the reason that no new action potential can occur is because the sodium gates are inactivated. Now, I want you to imagine that you went to the bathroom, you flushed, then you waited like a minute or so, okay? If I flush it again now, I'm able to get a second flush. It's not gonna be as strong as my first flush, but I can get something, right? And that is the relative refractory period. So the relative refractory period is if a signal is strong enough, it can elicit an action potential, even though the cell isn't fully recovered and it isn't back to its resting state yet. Okay, so absolute refractory period, no action potential, no new action potential can be sent, regardless of how strong the stimulus is. Relative refractory period, I can send a second signal as long as the stimuli is strong enough. Okay, so again, we mentioned this all or none phenomenon. I told you I'd come back to it. Again, with the all or none phenomenon, yes, we're sending a signal, or no, we're not sending a signal. There's no strong signals, there's no weak signals, okay? You're either in or you're out, okay? But, you know, based on what we know about the nervous system and neural integration and our ability to create coordinated movements and lift things up of varying forces and receive different stimuli of varying intensities, right? We know that we must be able to modify the intensity in some way, right? So even though one action potential is sent, it's not strong, it's not weak, it just is. There's no way to create a weak one or a strong one. We can vary the intensity in a couple other ways. We can, if it's a strong signal, we can increase the frequency of sending the signal, okay? So I'm sending the signals as fast as I possibly can, many in a row, okay? That increases my perception of the intensity, okay? The second way I can modify the intensity of a stimuli is to activate more motor neurons, okay? So I can also get other motor neurons sending signals, and that will do the same thing, right? So again, if I want to have a large change or a large effect, or it's a high intensity, I want to have 1,000 action potentials. So I can send a lot of them really fast, and I can also get more motor neurons involved so that they're sending signals as well, okay? If I have something of a lower intensity, maybe I only want to send 40 action potentials. Okay, I'm going to send them at slower frequency, and maybe I'll only involve 3 neurons versus 20 that I might have involved for something of higher intensity. Okay, so again, the ways that we vary intensity of stimuli is frequency of action potentials sent, and also activating more neurons. Okay. How fast can we send a signal? right? So the nerve impulse can travel down the axon very quickly. So again, we said that the action potentials will be determined kind of at this axon hillock, which is occurring here at the edge of the cell body, and we're going to send it down the axon. Okay, how quickly or the speed at which we can travel down the axon is based on two factors. Okay, hang on. Sorry, I couldn't find my notes for this section. One factor is the diameter of the axon. The other factor is if it's myelinated or not. Okay, so here you can see the myelin sheath. And if I have myelin, that allows me to move the signal faster. And if the diameter of the tube or the diameter of the axon is larger, that allows me to send a faster signal as well, because there's less resistance to the signal, basically, if there's a bigger tube. Okay. Okay, so here you can see a little more detail about the myelin sheath. So again, the myelin sheath is kind of like this fatty covering over the axon, and it's formed by specialized cells known as Schwann cells. And the myelin sheath is not continuous, but it has gaps, and these gaps between the myelin sheath are known as nodes of Ranvier. Okay, and if any of you are Spanish speakers or have taken some Spanish before, you might know what Ranvier means, or I'm sorry, Ranvier is French, I'm sorry. So these nodes of Ranvier, again, are spaces within the myelin sheath where we can send the signal. And I'll talk about the Spanish part in just a second, it's coming up. Let's see. Okay, so saltar or saltar is the verb for to jump in Spanish and in Latin as well. And so in order for me to send a signal fast when I have a myelin sheath, I'm going to do something called saltatory conduction. Okay, I'm going to flip back to the last slide so I can show you what this looks like. So basically, the signal starts here at the axon hillock, and I'm able to jump from node to node. And again, the jumping of the signal through saltatory conduction allows me to send the signal faster than if I didn't have this sheath. Okay, so this fat sheath, this myelin sheath, allows me to send a faster signal. Okay. Okay. Anything else? Yeah. Okay. Here you can see another image looking at saltatory conduction. So again, underneath the myelin, we're not transmitting the signal. We're simply choosing to jump that signal from node to node. Okay, so it's going to move from node to from node to node, as you can see here. So once we've sent the signal down the axon, it reaches the terminal or the axon terminal of that neuron. And the terminal is going to have an interaction with somebody else. In this case, you can see a second nerve cell. And this interaction is going to create something known as a synapse. Okay? And a synapse is simply a junction between two neurons. And this will allow these cells to communicate with each other. Okay. One thing to note about a synapse is they don't have a physical interaction. So I know it looks like they're touching each other and they're pretty darn close, but there is actually a gap between each of these axon terminal units and each of the dendrites shown in blue. Okay. Again, how do we send the signal from red neuron to blue neuron if they're not actually physically touching? We have neurotransmitters, and neurotransmitters are a chemical that's released by the presynaptic neuron, which is the red one here, to cause communication or signaling. Okay, these neurotransmitters can be either chemical or electrical in nature. In an electrical synapse, the electrical activity of the presynaptic neuron affects the electrical activity of the postsynaptic neuron. Chemical synapses are going to utilize neurotransmitters. So they're going to release a neurotransmitter into this little space, and then that neurotransmitter will be picked up by the blue neuron afterwards. Okay. So again, these synapses can be excitatory or inhibitory depending on the signal that you are, receiving. Again, presynaptic is the one sending the signal, postsynaptic is the one receiving the signal. I can be both pre and postsynaptic. Okay, so imagine like a train here. So you have 1, 2, 3 cells lined up. Okay, so this cell is postsynaptic to this one, which was presynaptic. Okay, pre just means I'm sending a signal, post means I'm receiving. Okay, so he's postsynaptic, he likes the signal, so he wants to send it on to his next friend. So this is his presynaptic terminal, and this is a postsynaptic as it relates to that neuron. Okay, so again, you can be both pre and postsynaptic. It just has to do with who's receiving information and who's sending information. And you can do both, but remember, it is a one-way street. Okay, so this postsynaptic neuron can only send information down to this next neuron. It cannot send information back up the channel. Okay, they can only flow down. It's a one-way road. Okay. Okay. So again, the synapse is a site of an action potential transmission from one neuron to another. And at the terminal end of the neuron, there contains something known as synaptic vesicles. And these synaptic vesicles are going to be like a little backpack, basically. And within that little backpack, we're going to carry a neurotransmitter. Sorry. Oh, goodness. And the neurotransmitter is going to allow us to send a signal on to the next neuron. Okay, so here you can take a look at what a chemical synapse looks like. So here you can see the presynaptic neuron or the axon terminal. Okay, and within the axon terminal, I have synaptic vesicles. And these synaptic vesicles contain a neurotransmitter, which is like those little bubbles inside. And when I'm ready to send the signal, I'm going to dock onto the edge of this presynaptic axon, and I'm going to release that neurotransmitter into this cleft or this space here. And then that neurotransmitter can have an effect on this postsynaptic cell. Okay. So again, when we think about how does this happen, this just kind of puts that into words. So again, those neurotransmitters are produced and stored in vesicles at the axon terminal. So again, those neurotransmitters are like in those little backpacks, like ready to go all the time. And when the cell is stimulated, calcium is going to rush into the axon terminals, and this is going to stimulate the vesicles to move, translocate, or like basically move to the edge of the membrane, that terminal membrane. The neurotransmitter is going to then be released into the junction via a process known as exocytosis, or basically like the dumping out of the backpack into this cleft. Okay. So once that neurotransmitter is like dumped into the cleft, then it'll have an effect on that postsynaptic neuron. Okay, so let's say I want to stop the signal. Like eventually I want to stop sending this signal to the next guy. And so what do we want to do? So I need to terminate the signal in the chemical synapse. So I need to remove that neurotransmitter. And this can be accomplished in 3 ways. Okay. Number 1, diffusion of the transmitter from the cleft. Number 2, we'll see degradation of the transmitter by enzymes. So enzymes are going to like break it up a little bit, like they're going to like digest it, kind of. Think of it that way. And then number 3, reuptake into the presynaptic cells for reuse. Okay. So again, I'm going to have some diffusion occurring. I'm going to like kind of break down those neurotransmitters, and then I'm going to ship them back to where they came from so that I can rebuild them and kind of reuse them. Okay. Receptors in the postsynaptic cell are removed from the membrane, so the receptors that were there ready to receive the information from those neurotransmitters are going to like recess back into the cell. So they're not available for binding at that particular time. Okay. Again, how do I activate this postsynaptic cell? This postsynaptic cell is going to be receiving lots of different stimuli, most likely, and it's going to receive graded potentials because of these signals. Okay, so these can be excitatory in nature. They can also be inhibitory in nature. So the inhibitory cells have a tendency to hyperpolarize or take things further away from threshold. And the excitatory stimuli or the excitatory signals are a little bit depolarizing, right? So they're a little bit excitatory for the cell. Okay. So here you can see an excitatory signal. Again, I don't quite reach threshold, but it did increase or have depolarization occurring in order to, have an effect. Here you can see inhibitory. So again, took the cell a little bit further away from that threshold level, as you can see here. So then we have this deal known as synaptic integration. And with synaptic integration, again, remember that I'm receiving information from probably a lot of places, okay? So I want to kind of sum up what I'm receiving from many different cells, okay? So here you can see 2 excitatory synapses and 1 inhibitory, okay? So let's take a look at what happens when A sends 2 signals, okay? So I get a little bit of depolarization, and then there's enough time in between the signals that I go back down, and then I get a little bit more excitation here, okay? If I were to send those same signals a little bit faster, so they were closer together, I get a little bit of summation, right? So the cell goes up, it starts to come back, but then I get a second signal, and so I'm able to increase slightly more, okay? I can also sum up A and B, right? So if A and B both send excitatory information, notice that that is enough to elicit a greater positive change in comparison to when it was just B or just A alone, okay? Now, if I send both A and B rapid fire, so a little bit faster, okay, I'm able to get this excitatory signal all the way up to threshold. And once I reach threshold, then the cell decides, yeah, I'm going to send the signal on. Okay, so all of this information will be summated here at the axon hillock. And if threshold is reached, then we're able to send that signal down the axon next. Okay. Again, notice that we're receiving information from C as well. So if C is inhibitory, that takes me further away from threshold. Even with A and C both releasing signals at the same time, they like cancel each other out, right? So if I receive inhibitory and excitatory, it has to be summed together in order for us to determine if it's enough to elicit a change. Okay, so here you can see the neuromuscular junction, and again, we'll be talking about the nervous or the muscular system and how this relates to how we can tie together the nervous system and the muscular system. But the neuromuscular junction is the site at which the alpha motor neuron synapses with the muscle fibers within the motor unit. So again, here you can see an axon, and here are the axon terminals here, and they're going to have an interaction with each of these individual muscle cells, okay? So in order for me to send this signal from the neuron down to the muscle cell, okay, these are the steps that need to occur. Okay, so the action potential is spread down the neuron axon, okay? The action potential then will reach the axon terminal, and the terminal will release a neurotransmitter known as acetylcholine, and this will be released into that synaptic cleft, or that kind of gap between the neuron and the muscle cell. Acetylcholine binds to the receptors on the muscle cell wall, and the acetylcholine causes sodium channels to open on the muscle cell membrane and allows that excitatory possibility to then happen. Okay, so sodium is going to rush into the muscle cell that causes depolarization of the muscle cell, and the action potential is formed. The action potential will then spread down the T-tubules of the muscle, which we'll talk about when we get to the muscular unit, and then muscle contraction is ready to occur. Okay. This is kind of what that looks like. So again, here you can see the neuron here, and here you can see the muscle cell or the muscle fiber down below. Okay, so again, action potential is sent down here. We can see saltatory conduction occurring. That signal is jumping from node of Ranvier to node of Ranvier over the myelin sheath. Once it reaches the axon terminal, that stimulates calcium to come in to the axon terminal. The movement of calcium into the axon terminal causes our synaptic vesicles to translocate over to the edge of the cell. So basically they're just going to like move over to the edge. They're going to dump their contents of their little backpack out into the cleft here. So again, acetylcholine is now entering into the synaptic cleft. Okay. That acetylcholine is going to bind to a receptor on the muscle cell, and that's going to cause sodium channels to open. Sodium rushes in, and that causes an excitatory signal to be sent to the muscle fiber. Okay. Just one last kind of slide to mention. Some of you know, maybe not all of you know, that I am an avid runner, and I wanted to share with you this concept of a runner's high. Okay. So here is me and 30,000 of my friends at the Boston Marathon. And again, the reason that I chose the runner's high to kind of use as an example is because it's freaking awesome. So I want you guys to all get out there and get it. And again, you don't have to do running in order to get the same feeling. You can get it from any type of exercise, really, and actually from music as well. So people find the same types of neurotransmitter release when we do singing as well. So it's kind of interesting. So basically, what is a runner's high? It's like a euphoric feeling that washes over you. And basically what's going on is you have endorphins that are going to bind to receptors that chemically block feelings of pain. Okay. So these endorphins that are released are neurotransmitters. They're known as norepinephrine, dopamine, and epinephrine. And these neurotransmitters are going to help reduce depression. They make us feel happy. Those of us that exercise regularly are significantly less likely to experience depression because of these neurotransmitters. So again, I want you to kind of imagine the synaptic clefts and being able to send these particular neurotransmitters into those clefts, and again, it makes you feel really good. Maybe you've experienced like a day where you're like, oh, I just don't really feel like exercising, and then you go do it and you get done, you're like, you know what, yeah, I feel like really good, I just feel a lot better, I'm glad I did that. Again, the reason for that is the release of epinephrine, norepinephrine, and dopamine. Like I said, can be experienced in a wide variety of activities. It doesn't have to be running. You can get the same response in any type of vigorous exercise, and also singing in a choir. So there's that for you. Let's do a stop share. That is it for the nervous system. Again, I would encourage you to spend some time kind of laying out those kind of basic components that we talked about that are important for establishing that resting membrane potential, and then thinking about what happens when we open those channels to allow an action potential to occur. So again, those are kind of the two major takeaways from this unit. I hope you have a great day, and I will see you soon.